Hello, this is Richard Walker from Lucidate and welcome to this second video on Ethereum and decentralized finance. In this video, we're going to introduce Ethereum smart contracts and take a look at Solidity, a language for writing contracts on the Ethereum blockchain. A good way to think of Ethereum is as a decentralized, distributed global computer. This computer stores all its data and all its transaction history on a distributed ledger. A transaction on the Ethereum blockchain can be one of three things: transferring Ether from one account to another, deploying a smart contract to the blockchain, finally executing, the technical term is calling, a smart contract. Let's pick a smart contract example. We'll look at an up and in barrier option. Recall that a European call option gives the option holder a right to buy an asset at a certain price on a future date. The price is the strike price of the option. The option holder pays the option writer premium in return for this right to buy at the strike price. If on exercise of the option the asset is above the strike price, then the option is said to be in the money. The option holder can purchase the asset from the option writer and sell in the open market at a higher price. If the asset price is below the strike price, then the option expires worthless. The option writer keeps the premium in both cases. A knock-in option has an additional feature, a barrier. The option will not knock in until the price reaches the barrier. Even if the asset is above the strike price upon expiration, the option will expire worthless if the barrier has not been triggered. Barrier options typically have lower premiums than vanilla options to account for the fact that the barrier increases the chances that the option will expire worthless. We can illustrate how this process from option writing straight through to settlement can all be handled with smart contracts on the Ethereum blockchain. An initial smart contract will contain the details of the barrier option. This will contain all the account details of the holder and writer. It would also detail the attributes of the option, including the underlying, the strike, and the expiry date. If the barrier is triggered, then this smart contract will create other smart contracts. One might be to handle payments of additional premium, rebates, or financing costs. The other would be the call option. All of this would happen automatically on the distributed ledger. Once the contracts are written, they are immutable and cannot be changed. The entire Ethereum blockchain can be visualized as a distributed supercomputer with interaction between loosely coupled smart contracts. No central party is in control. Users have the option to make use of as much of the existing functionality as they wish, or write their own. As each contract is added, the capability of the whole network is enhanced. The code is the legal contract, and the legal contract is the code. Entire enterprise applications can be built by composing existing smart contracts. Ethereum has created a special purpose programming language for this distributed supercomputer. This language is called Solidity. In this video, we will explore the key concepts of the Solidity language. These are the native features that make it suitable for developing decentralized financial applications. Solidity doesn't pretend to be a general purpose programming language like Python or Java. It is specifically designed to allow development of smart contracts to build DeFi apps on the Ethereum blockchain. Consequently, there are some really useful features that are built into the language to make it easy to use for DeFi apps. We will explore these in the remainder of this video. In the next video, we'll show how to implement a smart contract to represent your own cryptocurrency. In terms of the aspects of the Solidity language that make it super easy to deploy DeFi apps, we will look at the following three topics. Firstly, accounts. These are purpose-built for finance. 2, global objects and variables, making dApp deployment simple. 3, Modifiers and require statements. These implement security and gas saving. Accounts, purpose-built for finance. On the Ethereum blockchain, there are two types of accounts: externally owned accounts and contract accounts. Both types of accounts have addresses and public keys. Both can contain crypto assets such as Ether and have balances accessed by the balance attribute. Only externally owned accounts have and are controlled by a private key. In contrast, contract accounts have no private key and are controlled by Solidity contract code. With two types of accounts, contract accounts and externally owned accounts, there are exactly 4 combinations of account transfer. They are: 1. External account to external account. This would be the case for things like payments or bank transfers. 2. External account to contract account. As an example, this might be used to fund an option smart contract with premium. 3. Contract account to external account. A good example here is to receive payments from a derivative smart contract. 4. Contract account to contract account. If an option is exercised, some funds may move from the first contract to the second as initial margin. There are actually only 3 ways to interact with an Ethereum blockchain. Firstly, account transfer using one of the methods just described. Secondly, deploy a smart contract. And finally, use an already deployed contract. Global built-in variables, making app deployment simple. As mentioned previously, Solidity is specifically designed to build smart contracts and DeFi apps. It comes with some incredibly useful objects and variables that are built into the language to make interacting with the blockchain simple and straightforward. These built-in objects include the transaction object, from which we can get the transaction gas price and the original account that kicked off this particular chain of transactions. The message object, among other things, we can get the message sender's address, the message value in Ether, and the gas used in this message. Addresses, we can send or transfer a given amount of Ether to an address. Call, this will call functions in other contracts and libraries at the contract address. The block object, from this we can see the block height, the block miner or validator's address, the gas limit, the block difficulty, and the time this block was mined. All of this information can be accessed directly within any smart contract. Modifiers and require, security and gas saving. Modifiers are a great addition to Solidity. They're analogous to decorators in Python. There are many areas where modifiers are useful, but I want to draw attention to 2 in particular. Firstly, security. Secondly, gas saving. Modifiers are frequently used in conjunction with a require statement. In Solidity, a require statement has to be true, otherwise the function terminates with an exception. From a security standpoint, modifiers are extremely helpful in providing a single place where access, permissioning, and control logic can live. It becomes straightforward to establish ownership, access, and execution rights, as well as more complex security measures, such as multi-signature contracts and haltable, stoppable contracts using modifiers. The code on your screen shows a simple example of this modify and require functionality. When the code is deployed, the constructor sets the contract owner variable to the account of the contract deployer. The only owner modifier asserts that the caller of any function that implements this modifier must be the contract owner. The change price function implements this modifier. If any account owner other than the contract deployer attempts to run this function, then the change price will terminate with an exception. Another great feature of modifiers is that used correctly, they help save gas. It's usual practice to execute the control code in a modifier before the rest of the function is implemented. You bail out at the start of the function before any gas is consumed. As funds are routinely changing hands in smart contracts, and as smart contracts are immutable and unmodifiable once deployed, Solidity coding requires great care and thorough testing before deployment. There have been several unfortunate examples where less than robust code has been deployed, and this has led to funds being stolen. Use of modifiers and require is the first line of defense against malicious use and bad actors. So in conclusion, in this video, we've introduced the Solidity programming language, a powerful, high-level language similar in syntax and structure to Java and C++. Unlike those multi-purpose languages, Solidity is specifically designed to write DeFi apps on the Ethereum blockchain. As such, it has many useful built-in features that aid dApp deployment. These include accounts, both externally owned and contract accounts. Solidity also features objects and variables that provide information on the state of the blockchain from anywhere within a smart contract. The message and transaction objects are particularly useful in this regard. In the next video, we'll see how some of these key elements are used as we walk through a simple yet functional smart contract to represent our own cryptocurrency.